we can break down what root mean square comes from. And that phrase comes from so we have some voltage, which we have VA cosine of omega t. And what we do is that we take, well, first let me write this out. This is an integral for just one period of our function, which is VA cosine omega t. So the root comes from this 1/2. The mean is the integral for one period. And the square comes from squaring our function. We would pull the VA squared out, so that would be VA squared over t, integral of t, 0 to t. And we use our trig identity again. When we have a cosine squared, we could say it is 1 plus the cosine of 2 omega t. And that's over 2 dt, and that would all be square rooted. And if you take the integral of a cosine over one period, this is an average. So we're taking the average of this 1 plus cosine function. And we already talked about the fact that if you take an average of a cosine, it's 0. So then it would be VA squared over t times the integral of 0 from 0 to t. It'd just be 1/2 that is left, since that would go to 0. dt 1/2. And so we would end up with fairly simple integral to do. We'd have VA squared over t times t over 2. And these cross out, and what do you get? Oh, and this, of course, is rooted. You end up with VA over the square root of 2. This is our root mean square value, just like we said it was. So we have our average power. We talked about instantaneous power. We have root mean square values for voltage and current. So let's look at complex power. So complex power we'll actually call S instead of P. We have some Vs. We have some load, some simple circuit. And our load is an impedance, so it could be ZL can equal ZR plus J times ZI. So this has a real component and an imaginary component. So with this simple circuit, if we're looking at the power of this load that's dissipated across this load, then we could say the complex power of the load is VL times IL. And that would be what we just found, which would be the root mean square values. So, complex power, S, would be VL times IL star, where this is the complex conjugate of the current. So it'll be VRMS times IRMS complex conjugate. Let's kind of break this out a little bit. Our voltage, we said, is VRMS, and really I should say that these are phasors, right? So it would be VRMS e to the j omega t plus a phase as far as voltage goes, and the current would be I RMS e to the negative j omega t plus a phase of the current. And it's negative because we're doing the complex conjugate. So if we were to say, okay, V times I, complex conjugate, we should get VRMS times IRMS e to the j. And of course, when you multiply things together, you get to add. So you get an omega t plus the phase of the voltage minus omega t minus the phase of the current. You get V times I star equals VRMS, IRMS, E to the J with a phase difference between the voltage and the current. So this again is complex power, and our phasors turn into, when you multiply the voltage and the current, they turn into this equation with a difference in the phase from the voltage and the current. And this difference of phase between the voltage and the current is the angle of impedance. By now you're probably like, where did that come from? We'll come back to this as we draw it in complex space. But just take it as that this has to do with our impedance value. So our complex power has a phasor form. So you could say SL is VRMS in phasor, IRMS. This is its phasor form. Then you can do this in Euler form. SL is VRMS, IRMS, and it'd just be EJ some theta, where theta is the phase difference, so that's the angle of impedance. This is Euler form. And then we have this complex power in rectangular form. Rectangular form, if you remember, would be multiplying times the sine and cosine. So it'd be VRMS times IRMS, times the cosine of this theta, plus J, I'll put it down here, plus the imaginary part, which is J, VRMS, IRMS, times the sine of theta. And again, theta is the difference of phase. So, if we put this in rectangular form, we have defined two other components of power. So our complex power has the real portion, which has the cosine of theta, and the reactive portion, which is the imaginary, which is from the sine of theta. So we have P and Q. Real power is units are in watts, and reactive power has different units. Reactive power has VAR unit. There's one more type of power we should know, and that's the apparent power. And the apparent power is the absolute value of S, or the magnitude. So just like with any complex number, we take the real part squared and the imaginary part squared and square root it, and now we have the apparent power. And there, that unit is in VA. Let's look at this in complex space. Like I mentioned, might be easier to understand everything. So in complex space, we have our complex number, our complex power S. In rectangular form is P plus JQ. So P is here, it's along the real axis, JQ is along the imaginary, just like we saw before with complex numbers. So P would be the cosine of that triangle with the magnitude of S. So that is, this is apparent power. Apparent power is the length of this line, so it's the magnitude. So you take the magnitude times the cosine of the angle of Z, the angle of impedance, which was phi V minus phi I, right? Then we get the real power. If you take the sine of it, which is here, the magnitude times the sine of theta, then we have Q, and that's the reactive power again. So this is the what power is in complex space. Now we have one more parameter, and that is the power factor. And the power factor is real power over apparent power. So this is the cosine of theta. Okay. So the power factor lets you know whether you have an inductive load or a capacitive load.